Welcome. In this session, we'll continue the discussion on how to find the inverse Laplace transform. And in other words, if we have to find x of t from x of s, and suppose x of s contains a term of quadratic form. So if we how do you express it in this product of that s plus a s plus b form, right? So this time we'll see the case of if the roots of that quadratic term are repeated roots, right? So to illustrate this, what we'll do, we'll take an example here. Let's suppose x of s is equal to s plus 1 into s plus 4s, sorry, s square plus 4s plus 4. So this is an example, and our goal is to find the inverse Laplace transform. So what we have a quadratic term here, right? So how do we write the partial fraction of this? What we do, we'll first find the factors of this. Now, if you remember from the previous class, I told you if you have a quadratic polynomial or quadratic equation in x, how do we find the roots? We simply say x is equal to minus b. There will be two roots because this is a quadratic polynomial. Then the roots will be minus b plus minus b square minus 4ac divided by 2a. Then if the roots are alpha and beta are this quadratic polynomial, then we can write x square plus bx plus c. We can write it x minus alpha multiplied by x minus beta. So what we'll do, we'll find the roots of this quadratic polynomial here. So quadratic polynomial is simply s square plus 4s plus 4. So then we can write s1, 2. We can write it as minus 4 plus minus. Comparing with this, b is 4, a is 1, and c is 4. So it will be 4 square is 16 minus 4ab, 4ac, sorry, ac is 4, c is 4 divided by 2 multiplied by 1 because a is 1. So it will be minus 4 plus minus 16 minus 16 divided by 2, that is equal to minus 4 minus 4 plus minus under root of 0, that is 0 divided by 2. That means the roots will be simply minus 4 divided by 2, which is equal to minus 2. That means both the roots are same. In other words, the two roots of this are s1 is simply minus 2 and s2 is simply minus 2 also again. So s2 is again minus 2. So roots are of this quadratic polynomial or quadratic equation are same. Then we can say, then we can write s square plus 4s plus 4. We can write it as s minus 2, that is s plus 2 and s plus 2, which is same as s plus 2 whole square. So substituting this back here, we can write x of s as, so x of s is simply s plus 1 divided by s into s square plus 4s plus 4. Now we can write it as s plus 1. And for this term, we'll substitute this. So we'll say s into s plus 2 whole square, right? Now our goal is to write the partial fraction expansion of this now. So how do we write the partial fraction expansion of this? Right. So if we have a quadratic square term here, we write a1 by s, a2 by s plus 2. Then we write also a third term, that is s plus 2 whole square, right? This is how we write this partial fraction expansion, right? So we have three terms here, 1, 2, and 3. So we write the three factors here. We have three factors here. We write it in the three terms. All right. So what we do after this, to find the value of a1, a2, and a3, our goal is to find a1, a2, a3. We'll multiply both sides by this denominator term. So multiplying both sides by s into s plus 2 whole square. After you do that, when you do that, from this s into s plus 2 whole square will cancel. You will be left with s plus 1. That's equal to a1 s plus 2 whole square plus a2 s into s plus 2 plus a3 times s, because s plus 2 whole square will get cancelled. So after we do that, to find the value of a1, a2, and a3, we'll make the two terms go to 0 and find the value of at a time a1, a2, and a3. So what we'll do first, we'll put s equal to 0. So if I put s equal to 0, this term is 0 because this has s here, this has s here. So that means this is 0 plus 1, that's equal to a1 into 2 square plus 0 plus 0, because it will be 0 plus 2 whole square. So that's 4. So that means a1 will be simply equal to 1 by 4. Now to find a2, let me find first a3. Before finding a2, we'll find a3. So we'll put s equal to minus 2. If I put s equal to minus 2, this term is 0, this term is 0. Then we'll get a3. That means minus 2 plus 1. This is equal to 0 plus 0. a3 times minus 2. So it will be minus 1. This is equal to a3 times minus 2. That means a3 is equal to minus 1 divided by minus 2. That's equal to 1 by 2. So we have found a1, we have found a3. Now next we have to find this a2. So how do we find a2? Now to find a2, what we'll do, we'll write it, we'll first expand the terms in this. So what we have, a1 s square plus 2s, sorry, it is 4s. So when we expand s plus 2 whole square, if we do that, it will be s square plus 4s plus 4 plus a2 s square plus 2s. When you multiply this s by s plus 2, a3 times s. So what we'll do, we'll compare the constant terms here. What we have the constant to find the value of a2, sorry, not constant terms, we'll compare the s square terms. S square terms on both sides. We don't have an s square term here. We don't have an s square term here, but we can add that. We can say this is 0 s square term. So this doesn't make any difference. Also here, this does not have s square term. So we'll say 0 s square term. So this will make no difference. So if we compare this, so we'll say 0. So the coefficients will be get compared. a1 times 1 plus a2 times 1, because the coefficient of s square term is here 1. So it will be 0 times a3, right? So 0 is equal to a1 plus a2 plus 0, right? So that means a2 is simply minus a1. So a1 we have found already, it is equal to 4. So a2 will be minus 1 by 4. This is what we did, right? So to find the value of a2, what we did, we compare the coefficients on both sides of s square term. Here the coefficient is 0, here the coefficient is 1, here the coefficient is 1, but here the coefficient is again 0 to find the value of this, right? You can compare the constant terms also, but since we have to find a2, there is no constant term here, so we cannot use that this time. But you can use s, you can use the coefficient sub s. So you can also find the value of a2 using this s term. So if you compare s terms on both sides, let me show you, the answer will be same. Compare s terms means coefficients of s terms, that's the meaning here. So compare coefficients of s terms we have. So if we do that, so coefficient of this term is here 1, so it will be 1 is equal to a1 times 4 plus a2 times 2, because the coefficient here is 2, plus a3 times s, coefficient is 1. So that means, because a1, a3 we already know, a1 is 1 by 4, so it will be 1 by 4 multiplied by 4, a2 multiplied by 2, plus a3 is 1 by 2. So it is 1 by 2. So this will be 1 plus a2 multiplied by 2 plus 1 by 2. So 1 by 2 and 1 is 3 by 2 plus a2 multiplied by 2. So a2 plus multiplied by 2 will be equal to 1 minus 3 by 2. That's equal to 2 minus 3 by 2. That's equal to minus 1 by 2. Then a2 will be equal to, dividing both sides by 2, it is equal to minus 1 by 2. So you get the same answer that you got by comparing the S square terms, right? So answer will be same. Whether you compare constant terms, whether you compare S square terms, you will get the same answer, right? So this is how to find the A1, A2, A3. So what we have after we find A1, A2, A3, if we have A2 is S plus 2 plus A3 is S plus 2 whole square. So substituting the value of A1, A2, A3, A1 is 1 by 4, A2 is minus 1 by 4, S plus 2, then A3 is 1 by 2, S plus 2 whole square. Now we know the Laplace transform of 1 by S is simply, inverse Laplace transform 1 by S is U of 2t. Inverse Laplace transform S by 2 is simply e to the power of minus 2t U of t. And inverse Laplace transform of 1 by S plus 2 whole square is simply t times e to the power of minus 2t U of t. Right? Because the Laplace transform of t e to the power of at is equal to 1 by S minus, sorry, so it will be minus. If it is plus, it will be minus. So it will be S of minus a whole square, right? So this is how we find the inverse Laplace transform. So writing the inverse Laplace transform, that means x of t will be simply equal to 1 by 4 u of t plus minus, it is minus here. So it is minus 1 by 4 e to the power of minus 2t u of t plus t times e to the power of minus 2t u of t. Now taking u of t common, we will be left with 1 by 4 minus 1 by 4 e to the power of minus 2t plus t e to the power of minus 2t u of t, right? So this is the inverse Laplace transform of this case, right? So what we had here, the roots are same. You can see the roots are same. Now because of this, we get an S plus a square term here. We get a term that is S plus a square. Here a is 2, so we get a term. Now how do we write the partial fraction expansion? We write, because there are 3 terms, that is S into S plus 2 and S plus 2. So we write the same way, but only thing is we start with a1 by the first term, then a2. Now pay attention to this. It is S plus 2 whole square. First we write a2 divided by S plus 2. Then we write a3 divided by S plus 2 whole square. If this was cube, so if this was a cubic term like this, so S plus a whole cube. So what we'll do, we'll write a1 by S plus a plus a2, S plus 2 whole square plus a3, S plus 3 whole cube, because these are 3 terms actually. That's how we write the partial fraction expansion. So when the roots are, sorry, this is not 2, this is a. So I'm confusing it with this. So this is a. So S plus a whole cube. So this is how we write the partial fraction expansion. This time we have repeated roots. Then there will be definitely term S plus 2 whole square. Now whenever you have a square term, there will be t involved. Always remember that there will be t involved. You can check, there is t involved. So when we have a term like this, 1 by S plus a whole square, there will be t involved. So it will be t e to the power of minus 80 u of t. Now if this was cubic term, so if we have S plus a whole cube, then the Laplace transform will be simply 1 by 2 t square e to the power of minus 80. Okay, it goes like this. Okay, check the inverse Laplace transform. Simply this of 1 by S plus a whole cube, you will get the answer, and it will be like this. But since we are talking about the quadratic terms, we have a quadratic polynomial here, and the roots are repeating, means we have the same 2 roots, right? You can check the roots are repeating here. the root is equal to -2 and -3. And in this case, we'll have a t term, and a t is involved here. Okay, I hope you got the meaning of this. Now, in the next session, we'll see if the roots are complex. So if the roots of this quadratic term are complex. So let me stop here. We'll continue the discussion of inverse Laplace transform in the next session.